Okay, so here is problem 1 or rather problem 0. This is very simple. So this is problem 0, just a moment. So again, we just had a rectangle and yeah, this was like a special case of what we had done in the last class. So there is this thing, and then there is a triangle, random triangle with one vertex on this vertical side. Okay. Let's label this ABCD. Now, if this is 1, you understand that triangle is 1, and this right angle, this small triangle is 3. Then we want to know this thing, question mark. So let's call this. So any one of you can tell. I suppose this will be simple. And if you could not do it, then you can also say what you have tried. You guys didn't try it? No, nobody tried it. No, yes. Okay. Then try it now. If you have not tried it, let's try it now. So like this AEF is a small triangle and FCD is a small triangle, but they are not good triangles, right? So you need to sort of complete the picture and maybe look at them as part of a good triangle. That's one way. So that is the way we are done. Maybe a harder version of this. So that complete the picture. Because this is the phrase we had. This was a slogan last time also. What happened today? Everybody's off. I don't know the answer, but why is it 4? You can say the reasons or yes.
So AD ABC is basically AEF plus EFC plus FCD.
Right.
And FBC is basically EFC plus EVC.
Right.
So EFC basically gets cancelled from both sides.
Yes, that's right. And then you get 4. Right. So this is good. Yeah, this is good enough, right? So as you have done, you basically looked at this piece and this piece as a part of a bigger, picture, right? And the other one also, it's kind of connected with that, and the intersection part, does not matter. That's what we are saying here algebraically, that it cancels out. But more fundamentally, it's the intersection part. It's the overlap part. So that doesn't matter. The rest of the part in the first in ADC and the rest of the part in PFC will be same. This is a simple problem. Okay. Yeah. So yeah. So this is very simple. I should know. You can also, we can also obviously do this purely algebraically. Like if you're not thinking at all, like if you just write X, Y, and Z, now you can just set up equations and solve. Okay. So that's one way, but this is very simple. And this setting up equations may not be very good. It may get very clumsy for harder problems. It may not also, but it's a much more elegant way the way we have done. So this was a very trivial question. Let's come to the actual question, so this is from some old Soviet kind of question. So this is problem 1 maybe. And this problem I had taken from the book. There's a book called Which Way Did the Bicycle Go? This is actually a problem in the book. I'm not discussing that problem, but and the bicycle. This is the name of the book. I don't remember the name of the authors. I don't have the book right now open, but if you Google, you will get. This is a very good book, which has puzzle type questions, you could say, but they are not really puzzles. They have mathematics behind it. Obviously, puzzles also have, yeah. But they are mathematical, but they are not really advanced, but they require some ingenuity. So it's a very good book, and it has unique problems. Like, Soviet times, they were really good at these things, and especially originality. So you can check this book out. There are sections which you can access, but obviously I'll whatever I do topic, I'll go topic wise and try to do. So yeah, that problem is taken from there. It's also there on the Cut the Knot website, but it's not very clear there. So let's draw the thing. Okay. So this is about a parallelogram. It should not throw you off, as I said last time, because parallelogram has the same features, where any triangle with one base as a side and other vertex on the other side will have half the area and so on. Yeah, but then inside this parallelogram, we decide to do something. We kind of make a star. Okay, we make a star. We make a random star. The vertices are. But tell me one thing: did you guys get the time to try these questions? Or no? Because no. Okay, then we'll try it now, because I just want to know so that I can set the pace. Okay. because yeah, it can happen. Unav, have you tried? Did you get the time to try them? No. Okay. Fine. So then we'll have to do it now. Okay. That's okay. Because I must know, right? So here is basically the region outside the star. So I'm just going slowly, but you are obviously thinking about it simultaneously. And there is this region outside the star. Try these problems. Okay, if you can't do it, that's not the point. Okay, when I was trying it okay, I didn't never tried this problem exactly when I was, years back. But I tried many problems and which I couldn't get anywhere. But I just spent hours sitting with it. Maybe I was not even thinking about it, but just sitting and staring sometimes. Okay, so that's important. It all will be useful. So basically, this region outside the star, okay, is this red region. But then there is a region inside the star, but we are interested in a region which is inside the pentagon that is formed. So you can always see the pentagon. There's a pentagon here. This pentagon. Okay. And let me just label this as. So the question was that the region outside the star and inside the pentagon, the difference between them is a constant. STU. Sorry, 1 second. So we want to say that the red region minus the blue region, the area, this is a constant. So basically, we just try to explore this. So let's think. So even though PQRS are not given, like no ratios, nothing is given, even then, this difference, the difference will be a constant. So basically, as the area of the red region increases, the area of the blue region also catches up. Okay, it's a bit like that. Is the blue region visible? Basically, I just want some observations. So all of us should make at least one observation, some different kind of observation which we have not made before about this figure. Obviously, DQC has half the area of the parallelogram. All that is fine. We know that. Some more observations. So then let me ask some questions. So here, if we take AQD, this triangle AQD plus this triangle CBQ. Okay. And also, when I'm giving these questions, if you find this too difficult, like you can't even get started, then you can just simplify the question, right? You can say, okay, I will take the point Q at A. Take the point Q at A, draw the new picture, and try the same problem, right? So that also you can do. I should do that, but you can also do that if I don't do it. Anyways, so now this will be doing it in a guided way. Let's see if we can do it together. If AQD and CVQ, if we add them, can we say anything interesting about this? Like, is it a constant? What is it? If it's a constant. Right. So it is half of the whole area. So that is important. Okay. Unab, do you see this? Good. Good. So then so what we can then try to show is like the red region is a bit strange, right? All of you would agree, right? It's like this part should have also been in the red region. It would have been good, right? So we will put it. We will put it in the red region, okay? So then we will try to show this, that ADQ, because this is a more natural question and it's an equivalent question. It's like we're completing the picture. If we take ADQ and then we take CBQ, so again, we have just completed the thing. We want to show that this, obviously, plus we shouldn't forget this thing, okay, minus, so what should I write here is a constant. So see, pay attention here. Initially, we have to prove that this red region minus the blue region is a constant, okay? Now you see, to the red region, I have added this little triangle PTS and this URV. You agree, right? I've added it to just, make it look like a more regular figure, regular triangles, made up of triangles. So I've added those two things to the red region. So you would agree I should also add them to the blue region. Is that right? Okay, yes. So see, initially the question is, we want to show the red region minus blue region is a constant, right? But the red region, if you see, it's kind of like the PTS is missing, right? PTS is missing in the red region, right? Similarly, URV is missing in the red region. So what I'm doing is I am putting them in the red region. I'm adding them to the red region. Okay, I am adding PTS and URV. Fine. Why I'm adding it? It's like a very obvious thing, right? To complete the picture. That's, I mean, you would also do it if you spend long enough time on this, right? So we add the two regions. But if I'm doing this and I don't want the question to change, obviously, then I should add it to the blue region also, right? Or I should subtract it also, you can say. So that's all, right? So this thing becomes three triangles, ADQ, CBQ, and DWC is there. Yeah, the new thing becomes this. And the blue region, instead of being this strange pentagon, it also becomes simplified, right? It becomes PWR. This becomes PWR. right? I mean, signs and so on, you can adjust. So then I will show that this is a constant. Okay, just see if this is okay first. Is it fine?
Yes, sir.
Okay, Unab, is it fine? If it's not fine, you should say, okay, any, because there are only two of you, and you should be absolutely clear what you're doing so that you can use these ideas. Please. Yes. So see, initially, so let me remove this thing. So how about Ishana? Can you explain? Can you try to explain this? Maybe that will be good.
Over this video, we have first added two small triangles to the left part.
Mm-hmm.
Then two triangles remain. But the ratio should be constant, so we have to subtract them from the blue.
Yeah, the difference should be constant. So we have to subtract them or add them to the blue part also. Okay.
Yes, so
So
we basically have to say that the three triangles minus PWR is constant.
right, we have to show. Okay. So you see Unab, right? To the red region, we are adding some things, and so we are also adding to the blue region. Yes. Yes. Right. And why we are adding is very obvious, just to make the question more tractable. So, okay. So this is a very obvious step. There is no magic in this. Okay. Now, how do you show this? So it's not done. This is this first step, maybe. But we do know that ADQ plus BQC, this was the observation, which kind of maybe motivated. So already we know that this part, ADQ plus CBQ, is equal to half of ABCD. Let me write it. I don't know if it will be useful. I don't know if it will be useful, but let me write it. So the question reduces to this.
Can we replace this by DQC?
You're saying to replace ABCD by 2 by DQC.
Yes.
This looks like a good step, right? We're bringing everything to, okay. So I'll just write it here formally to, this is same as DQC. That's just obvious. So yeah, let me be a little more clean. So we can remove that. So let's write everything. Okay. I mean, so this is DQC. Okay. Yeah, I also don't know what to do now. So this PWR is a problem, right? So okay, one more thing. Don't get too much stuck on any of these three. Be open to all three. Just think freely. Okay. Like the benefit of maybe the first one is that there is a lot more flexibility from here. You can still do a lot of things, right? The benefit of the second one maybe is that it is very simplified, like computationally simplified in the sense that now we need to only show, if you look at the second one, if you look at the second one, then we only need to show that this thing is a constant, dwc minus pwr. So that's the benefit of that. And the third one is another expression. It kind of bringing everything into one triangle, though pwr is still a little bit outside. So yeah, all three are there. Okay, they have different sense.
I don't think this statement can help us that much. WC is already in DQC.
Yes, I also think it is not very, yeah. So I'm also not in favor of that too much, right? I think the second one is the, so we need to, so second one is saying that we only need to compare these two things. So just maybe for a minute, focus on DWC and PWR and try to relate them. If you can show that the difference is constant or something, because that's what you have to show, right? Because ABCD by 2 is a constant. DWC and PWR. So you can just look at the trapezium, PRCD, right? Because you want to just focus on those two things. Just focus on the trapezium. And try to ignore the things that are not important. We just draw a new picture.
Can we say the ratio is constant because if PWR PNP were decreased in height, it will in a way affect the other two triangles, PW, P and WRC. So if we just replace W in a different position, one triangle's height will decrease and others will increase for the same.
But how do you change the W? By changing R, you're saying, or something like that? Or maybe you can just repeat the argument.
Input W is shifted a little, then the areas of both of them will change, but the difference should remain constant because if we see the other two triangles in this equation, PDW and RWC, one triangle A right will increase, this will remain.
Okay. By the same amount, are you sure about that? Oh, yes, by the same amount, right? Yes. Yeah, that also is correct because it's a, two sides are parallel. Yeah. So then what is the conclusion you draw from there? So you're saying that PWR and TWC, the difference should be a constant or in some way. Yeah, but that's still a vague thing because it's not proportionately, it's like the additively. Additively you should say, but then everything should change additively. And I think it is changing, but it is a little vague. Maybe with some calculations you can clarify that. But look at the second picture I've drawn. It's already there on the left side, but I've again drawn it. Now just look at PWR and DWC. What is their areas? So there's this trapezium, and you're looking at this PWR and DWC. It's not an isosceles trapezium, otherwise they are congruent triangles. But can we still say something precisely? Mhm. So we have already actually done this. I mean, what if it was a parallelogram? Okay, then they have isosceles. Mm. So, okay. So focus on this figure. And there, if you have this PWR and DWC, what can you say about them? How do you compare them? Like, so the claim is that there is a very simple answer. But then if you turn it into a parallelogram shape, then the area may change, right? And even if you keep the area same, I mean, you may not be able to keep both areas same, right? Of PWR and DWC. But you can simply just look at the same principle of base and heights. You can use the same principle of base and heights as we used in a parallelogram or in a rectangle earlier.
Median and single recording method sometimes present PDW and
That's right. But yeah, but that's not the case. But even then, see, you can say that PDR is same area, is same as PCD. Can't we say this? Same base, same height, right? And so we are done, right? And this is the common triangle. PWD, they are actually equal. The area is actually equal. You see, this thing, this blue thing, but they both can be completed to the same place. That was so simple, right? But we just missed it. Yeah. So in fact, they have the same, see, so very simple things building up to this big. So this problem totally is not so simple, not so trivial. Well, it depends, but like for us, maybe it's not so trivial right now. But it's made up of such simple things, right? So no, the area. See, so PDR and PCD. See, they have the same base PD and they have the same height. It's a trapezium. Right? They have the same height because they are between two parallels. Right. Yeah, that's the thing about trapeziums. Right? Yeah. Yeah. So maybe trapeziums. Yeah, we have never done, and maybe you guys have also not uh, seen them enough. Obviously, you've seen them, but maybe not seen them enough. Right. So this was the problem. Yeah. Yeah. It's a very wonderful problem. So then maybe let me ask you this question. This is a very simple question, and this is a homework. Okay, so this is a homework. Given given that half into base into height is the area of a triangle, and you understand what the base and the height means here. What base and height means. Given this, uh, prove the formula for area of trapezium. It's a very simple question, but there is something interesting lying in there. So that's why. Prove the formula for area of trapezium. So you should make your own trapezium, label it, and try to prove. Okay. One way would be to divide it into triangles and so on, but without, so maybe I'll say without, if you can. If you cannot, then just do it usually, but without breaking up the trapezium. Maybe some more interesting way, completing it to a triangle or something. Is the question clear? Right? Because you can always break it into triangles very simply. Right? You can break it into right triangles, do some algebra, some manipulations, and label and manipulation. Just some labels and just add, no manipulations actually, and you'll get the formula. But that's right, you can complete that also and write it. But see if you can do it in a different way by maybe creating a triangle using some similarity or some more interesting stuff. Okay, try it. It's a very simple question, but yeah, good. Try these questions that I'm giving, and if you get stuck, just message me or mail me or just message me, and I will try to give you some hints if I can. Okay, so yeah. Okay, so this was the question. Now here is a more hard question. So here is a parallelogram. Oh no, not a parallelogram. Just give me 1 second. Yes, you have question? Any questions? Yes, right. So take a trapezium. Again, this is a problem on trapeziums. Now, again, as I'm saying, if you cannot do it like this, take an isosceles trapezium and do the problem. But try. Okay, make some progress. Means try something. Now we are doing an interesting construction. So what we're going to do is from one side, we are going to the next side, and we'll go to the midpoint of the next side. So rather from one vertex, we'll go to the midpoint of the next side. Okay, and we do this thing. So from this vertex, we go to the midpoint. Just a second, I get this sweater gives me a little allergic, it's itchy. And then again, yeah, so they will not be parallel, but it's just midpoint. Okay, just joining with the midpoint. And then from here again, so these things 1 minute, these things need not be parallel, right? None of these lines, or maybe some of them might be, but maybe not. Yeah, as of now, I don't think any of them are parallel. Okay, but if you make an isosceles trapezium, then maybe. So you have to figure that out. So then this is the construction. Now we have this thing. So I have this little. So we have this little pieces here, right? This thing. So all those little triangles, the corner triangles. Okay. So we want to show, and you can figure out this answer on your own. If you, I mean, just what we need to prove, if you just take a square or a parallelogram. Okay. So you can take that special case also and try first. If okay. and this pink region. So the sum of this area of this pink regions is in fact equal to the area of this green region. Okay. So the problem is show that the area of the pink okay. These questions actually, if you look at them physically, like especially the star problem one side, if you move the, so I'll just save this first. If you go back to the, so I'll come, okay. So 1 minute. Just wanted to say one thing. Yeah, like in this question, this question actually says some very interesting facts. Like, see, if you fix the q, if you fix the q, yeah. Now, if you, yeah. Now, if you move the r, let's say upwards, so let the p be. So that's another way in which you can reason it. Okay, intuitively, that will not give an answer in the sense that. So let's see, if you move the r upwards, then what happens? So if the rest of the things are fixed, then when you move the r upwards, then what happens? Area of the blue region increases, right? Right. So that then can we argue that the area of the red region also increases? It should, from what we have proved. But can we see that? That should be true. So which ones will decrease? The yes, right. Right, right. So, but then it turns out that in fact there is an increase, right? And you see, now this is like a physical kind of question, right? Some process in which it's happening, and they are against again and again spotting that it, both are like the increase in the red region is same as increase in the blue region. That's basically how the question is made, right? That both are increase at the same rate. But then to prove it just by physically, it's just seeing it, it's hard to prove, right? But then if when you frame the question like this, then we are able to prove it by just such simple methods. So that's it's actually a dynamic problem, which we are just proving it as one static instance, and we are able to prove it easily. Okay. So these are actually, deep questions. Some of them are actually done with those some mass point methods, but these are simple enough, so we don't need such things. And yeah. Okay, so I don't know, that questions which I wrote are gone. So I will send it again, okay? Because it will be there in the video, but I'll just take a screenshot of the video and I'll send you. Okay, you can also see, but you find it. Yeah. Okay, never mind. So those are the questions, and then we are done with that. Now I want to do one last question, which is a classical result, which I had given last time, which we did not discuss. So let's discuss that. Otherwise, it will be forgotten. Yes. So that problem is, yeah. So I thought I could bring it back, but apparently control Y does not work. So so let me just draw it again, right? That's not a problem. In the sense that we can see it. So it is like this. That is this trapezium. So what we are basically doing is from one side we are going to the midpoint of the other side. Okay. Then from one vertex. Then from this vertex we are going to the midpoint of the next of the, you could say, the opposite side kind of. Then from this vertex again we are going to the midpoint, and again we are going to the midpoint. Okay. So the lines may not be parallel. Okay, it looks parallel in this case. You have to check. They may be parallel. You have to see. Oh wait, let me just think. Will they be parallel? So if, yeah, let's just sort this out. So if this is equal to this, okay, and if this is equal to this, then does it imply that the lines which look parallel are parallel? Let me label them A, B, C, D. P, Q, S. Then is PB going to be parallel to DC? We will not use that. We will not use that. It's hard to say, right? In fact, mm, mm, yeah. So you can think about that also, okay? Yeah, you can think about it. But remember, it's a trapezium. So you can note that it's a trapezium. What we want to show, okay? So let me write this thing clearly. AP is equal to PD, and DS is equal to SC, BR is equal to RC, and so on, right? AQ is equal to QB, these things. Now, these corner triangles, we want to show that the sum of these areas of these corner triangles is in fact equal to the area of this quadrilateral in the middle. So the pink region is equal to the green region. First, see if the question is clear, and then just note it down. And it's based on the same principles like completing the picture and so on. So is the question clear? Oh, you have to show that the area of the pink region is equal to area of the green region. Okay. Now I could have given like area is 1, 2, 3, 4 and show the find area of this green region. But now we are not doing it that way. Yeah, so show that the green is equal to the pink. Okay. Again, it's based on simple things like completing picture, half the full, and so on, so on. Just try. Okay. Try to, I mean, even if you have other, I mean, obviously saying this to both of you, obviously, other things, just give some half an hour at least. Okay. Okay. You'll enjoy it. See, you can take an isosceles trapezium and try. You can take a square and try a square. You can see it. You will see it very simply. Then take a rectangle. Just do write it. Okay. Then see. Okay, and then ask for hints if you need. So then I'm erasing this. Okay. Now we come to this classical proof. So we are doing a area-based proof of the Pythagoras theorem. So this is let's say proof without words. Okay. So area-based proof of Pythagoras. So basically, we all know the theorem. If we state it purely geometrically, then it says that if you construct squares on these sides, on all the three sides of the side triangle, oh, yeah, this is a true square, okay? I use the shift button, the true square. So this is a square, and then again, this is a square on this side. Okay, so you guys know this, right? That now the area of the third square, let me just remove this, will be equal to the area of the other two squares. Let's do some labeling. Right. So what do we want to show? We want to show that ABED, this square, this is the square of that side, that's the area of the square, and plus BCHI, that's the area of the square on the base, or basically the square of the base. That is equal to this big square on the top. So this is what we want to show, and we understand that this is the Pythagoras theorem. Okay. Now, how do we show then that, how do we compare the area of these two squares with the bigger square? So we want to compare it with the bigger square. So we have to try to relate. Let's see. So you take a square, maybe take this ABED and try to relate it with AFCG. Somehow find a version of it in AFCGC. This proof you guys would have tried, maybe, I thought. It's also you can also find this in like NCRT even, maybe, right? This is there, I think. Or maybe now it's not there. I don't know. Maybe it is there. Let's think about how we can bring in ABED inside the square, inside the big square. That is the tactic. That's the first tactic. So remember, obviously, that this is a right triangle. So this is a straight line and these are all parallel. This is also 90, 90. So we have to slowly shift the ABED to AFGC. Now maybe we don't see a direct way to do it. Now one can just say it directly also, but we can slowly take parts of it. So in the sense that we can take this thing, we can take half of it, right? We can take this ADB, that's half of it. Now, can you shift ADB to the right? Can you somehow take it towards the square? So what if I divert your attention to ADC? How do you compare them? How do you compare ADB with ADC? Try to compare ADB and ADC. So it's just the same principles as we have used so far. Take your time, don't rush. Think, let's see. Yeah, so can you give, why do you think so?
Because it kind of looks like a parallel.
Yeah.
It's like it is divided in.
Oh wait, no, which is a no, no. A, that's not necessarily a parallelogram, right? ACBD is not necessarily a parallelogram. Well, it is in fact not parallelogram, because is BC equal to AD necessarily? No, right? Because AD is equal to AB.
So so
No, but if AD is not equal to BC, then you know it's not a parallel. So yeah. So see, it's not a parallelogram, but we have gone beyond that, right? We have already seen it applied in trapeziums, and we have seen a fundamental thing that is not about parallelograms. The fundamental reason why area remains the same is is when you have two things with the same base and they lie between two parallels or with the same height, same thing. They don't have to form a parallelogram, right? All these triangles will have the same area. This is the right. Okay, this is the place where we have reached, right? We have gone from squares and parallelograms to trapeziums to this general thing about lines and parallel lines and areas. Okay, so see, with that it's very obvious, then this is equal. So we are somewhere. So now we have ADC. Now ADC is our new friend. Right before we had ADB, but now we have ADC is the new auxiliary thing. Can we use that to travel to? So how do you use ADC to go to maybe the square or somehow relate it to something in the square? So you can try to relate it because AC is equal to AF and so on. Think. Take your time and think. Yes. So see now, see our ultimate goal is to relate the square ABED with something in the square in the big square, right? But then ABED that we have sort of related with easily related with ADB. But then we have said that ADB is equal to ADC, right? So now our focus is on ADC and try to relate ADC to something in the square, in the big square. something related to this. We want to further go towards it. So think about this. This is a subtle point. Maybe it's a new idea. So maybe I can try to say this. See, if you fix this point, fix the point A, and you think about rotating the triangle ADC. Fix the point A and rotate. So that's the axis, the point of rotation. Fix the point A and think about rotating the triangle ADC. Okay, I rotate it by 90 degrees and see where it goes. Okay, so I'll write the recipe. Fix A, rotate ADC, rather maybe I should say DSC, same thing, DSC, about A by 90 degrees. And tell me, where does it go? AC will land on AF, right? Where will AD land on? So you're rotating by 90 degrees, right? And so then we can say that ADC is congruent to ABF. Because when you rotate, you don't really change the congruency, right? Rotation will remain congruent. After rotating, whatever you get, it will remain congruent. But we're getting ABF. See, so this is a good way to see that things are congruent. Then you can obviously, then once you see it, you can reason it with the rules. But this is also an accepted rule. You're just rotating. So it's not an axiom, but it's obviously accepted. Okay? Yeah. So see, we are using these dynamic things to kind of reason that. Okay. So now where are we? Now we have come to, see, we are going around basically, literally, right? So now we have come to ABF, right? Now ABF is our new goal, is our new, rather the new point of attention. So ABF. So we have shown so far that ABD is, which is half of the square, small square, that is equal to, area is equal to ADC, and that is equal to area also equal to ABF. Now, how can we relate ABF with the square even more? We have kind of now entered into the big square. We have left the small square. We have entered into the big square. But what more can we do to go completely into it, into the square? Okay, rotate what? Mm, no, because see, BC is not equal to AB, right? BC and AG, so in this figure it may look same, but it is not same. So like you will see that a similar thing when you do with this, when you do with, so you can use the other part kind of, to guess how the thing will fit together. Okay. So when you look at BCHI, you can again use the same thing to say that BCHI will be half of, will be double of BCG. So ABF is equal to half of ABED. And in the same way, you will be able to say, please check it, okay, or convince yourself. In the same way, you'll be able to say that BCHI, half of that is equal to BCG. Okay, so we want to show that ABF and ACG, they are half of the big square totally. Right. No, it's BCG. I have written ACG, sorry. It's BCG, yeah. BCG, right? So now we want to show that BCG and ABF plus BCG is half of the big square. AFGC. This is not difficult, and this is your homework. There is no new concept again, but it's maybe a little tricky. You have to see. I just did the complement part also about BCG because then you may know how to fit the piece, okay, by looking at the total space available and so on and symmetry. So you see, but don't think that AB but BF is equal to BG. No, they are not equal. Okay, it's not an isosceles this thing. Okay, it's not an isosceles triangle, not an isosceles triangle. So this is your homework. So you would also need to then understand these things. So just make sure you've understood it. If you want, you can try it again yourself, or you can see it, but complete this. Okay, try to complete this. Yeah, so just maybe, yeah, take your time and try to understand this. If you have not, means if you have questions, just see. Otherwise, then the class is over. And so next time, should we discuss the inequality problems or should we do something new? I think maybe we should discuss the problems. Yeah, let's discuss the inequality problems so that it will be proper learning. So this give a bit more time to the inequality problems if you can. I will take a class on Sunday mostly. If not, then Monday. Maybe I'll take on Monday. Okay, so try them. Don't miss it. Okay, just try to get some time. Right. So then, is this good? Then I will stop the meeting if you have understood this. Or if you're still, then just okay. Okay then. So try the rest of the problems and then we'll meet on Monday. Okay. And ask me for hints if you need to on WhatsApp. Maybe you can just ask simple. Okay. All right. Thank you. Bye.